So in stoichiometry, we are obsessed with mole ratios. How do we find mole ratios? Or just look at a balanced equation. It's going to be the coefficients from the balanced equation, where in the previous unit we just kind of read it as 1 molecule of nitrogen, 3 molecules of hydrogen, forming 2 molecules of NH3 ammonia. But now we've kind of learned that we can't run that realistically in a lab. So instead of focusing on individual molecules, we're going to ramp it up and use the unit moles. Moles is a unit that represents a quantity of particles. And so if I had 1 mole of nitrogen and 3 moles of hydrogen, I still have 3 times as many hydrogen molecules. And that's the whole purpose of the ratio in the balanced equation. Now we can show that with a graph, where here they're looking at moles of reactants, which are the nitrogen and hydrogen, versus moles of NH3 ammonia. You could use the slope of the graph to find the mole ratio, which then should correspond to the ratio in the balanced equation. That if I found the slope, and let's say it was the ammonia versus nitrogen, the blue line, if I have a slope of 2, then that should correspond to the mole ratio, not a ratio of grams, which is what we learned in the last set of graphs, is that the mass is something we could graph, but it would not correspond to the ratio in the balanced equation. That ratio only corresponds to moles, or a unit that represents an amount of particles. When I look at moles of ammonia versus moles of hydrogen, that red graph, I get a slope of 2 to 3, which matches the ratio in the balanced equation. So when I look at all the different ratios I could pull from that balanced equation, we could compare amounts of reactants. So I could say for every 1 mole of nitrogen, there's 3 moles of hydrogen, or vice versa. Every 3 moles of hydrogen requires 1 mole of nitrogen. Or we can compare ratios of reactants and products. Every 1 mole of nitrogen produces 2 moles of ammonia, or 3 moles of hydrogen produce 2 moles of ammonia. So in question 10, they want to know how the slopes of the lines would look on a graph of moles of product versus moles of reactant for the formation of water. What if I had kind of a similar graph, but it was the synthesis of water instead of NH3? Well, now I would just look at my ratios. If I had like the slope, and it was going to be moles of water to moles of hydrogen, it should match the ratio in the balanced equation. So there's 2 moles of water for every 2 moles of hydrogen. So I should get a slope of 1. Okay, that makes sense. So the hydrogen and the water are always formed and consumed at a 1-to-1 ratio. Now let's say I do the same thing with the water, moles of water versus moles of oxygen. And I'd say, well, for every 2 water, there was only 1 oxygen. So my slope should be 2. And we don't have to use the ratio in the balanced equation exactly as it's written. We just have to keep the integrity of that ratio. So I could form 4 moles of water. I would then need 4 hydrogen and 2 oxygen to make 4 water. We could like double the ratio. We could triple the ratio. We could multiply the ratios by 10. We could half the ratios. I just need to keep the integrity of the mole ratio from the balanced equation. One way of proving that would be by graphing. Now here's the calculation that we're going to run. It goes back to our days of setting up mole ratios and proportions. And I get that sometimes this will seem really simple, which is great. If you get this here, Fantastic. All we're going to do then is just kind of ramp it up in the next couple sections. When we look at mole calculations, it's converting between moles of a reactant or product and something else in the balanced equation. Here, if we're using that reaction forming water, it says how many moles of oxygen would be needed to produce 25 moles of water. And so I like to go right down here. This is where the good stuff is. Like when we did mole calculations, you start with the quantity that you're given, the number and the unit. That's crucial. I'm not just going to write down 25. 25 what? Oh, it's 25 moles of water. Then I'm going to set up a proportion. On the bottom, it's going to be the unit that I want to get rid of. So let's say we're starting this off as 25 moles of water. I'm going to set up a proportion just like I did back in the mole days. The unit that I want to get rid of is going on the bottom. I don't want moles of water anymore. I already know how many waters I want. 25 moles. It says how many moles of oxygen. So moles of oxygen is what I want. That goes on top. Now what do you use on the lines? Well, back in the day when we were doing mole calculations, it was like moles and molar mass off the periodic table. Well, now when we're converting between different particles in a chemical reaction, the mole ratio is the ratio of coefficients from your balanced equation. So once you set up your proportion, then you just look at your balanced equation to say, okay, there's 1 mole of oxygen for every 2 moles of water. Moles of water will cancel, and then we multiply across the top and divide by anything on the bottom. So yeah, 12 and a half. 25 divided by 2. Oh, okay, I can do this, right? So check out number 11. In 11, we're going to use the same balanced equation, but this time we're going to look at moles of hydrogen. How many moles of hydrogen gas would be required to produce 25 moles of water? Fantastic. This is stoichiometry. When we're converting between amounts of reactants and products, you start with what you have, 25 moles of water, and then we're going to set up our proportion. The unit that I have goes on the bottom, moles of water. The unit that you want goes on top. How many moles of hydrogen? And now the numbers, I put the numbers in last. First, I get everything set up. Then the mole ratio is the ratio from my balanced equation. So between hydrogen and water, it's a 2 to 2 mole ratio. Oh, I think I like this. Moles of water cancel. 2 to 2, 1 to 1. 25 moles of hydrogen. And I could say, does that make sense? Well, yeah, this all makes sense. And that we don't always just produce 2 moles of water. What if I want 25 moles of water? Well, I still need to keep the integrity of that 2:1:2 mole ratio. So if I had 25 moles of hydrogen and 12.5 moles of oxygen, then I can produce 25 moles of water. We can either ramp up the ratio to make a larger amount, or maybe I could half the ratio or quarter the ratio if I wanted to make smaller amounts. But I'm always going to set things up hinging on this ratio from the balanced equation.